what can we say about memory usage of Prolog programs? Well, for one thing, it's not an inherent property of the programs as such, but depends rather on the Prolog system that we are using. And several system-specific factors have an influence on memory usage. For example, it depends on how the system internally represents Prolog terms and programs. And it depends on whether the system implements garbage collection. And of course also on how well the garbage collector works. And it also depends on the available system-specific optimizations, such as tail call optimization, stack trimming, and so on, which a system may implement and may also not implement. And it may also depend on other factors, such as the operating system, the available compiler features, and so on. And still, a few general points hold for all Prolog systems. Namely, they all must store Prolog terms in some way. And at least something must be stored so that control can return from predicate calls and proceed with the remaining calls in a clause. And logical alternatives must also be remembered in some way so that they can be tried on backtracking. So how can this be done? And for illustration, consider a simple stack-based execution model of Prolog. For instance, here are a few sample facts and rules. And we can implement the default execution strategy of Prolog with a stack that keeps track of alternatives that still need to be tried, where each alternative is a list of goals that we need to prove. For instance, suppose we want to derive whether the predicate P is true. Then that's a single goal. And so we represent it as a list of goals with one element. And that's initially the only alternative in our list of alternatives. And now each inference step transforms the current list of alternatives. Namely, it looks at the first alternative, which is currently the only alternative, and in that first alternative considers the first goal, which is P in this case. And it looks up all clauses whose heads unify with the goal. So in this example, there's only one clause for P, a rule whose body is the goal A. This means that P is true if A is true. And so the list of alternatives is transformed to a new list. Again, a list of alternatives where the goal is replaced by the clause bodies. And then it continues in the same fashion. Look at the first alternative, and within that alternative at the first goal, then find all clauses whose heads unify with the goal and transform the list of alternatives by replacing the goal with the clause bodies. So in this case, there are two clause bodies for A, and therefore we get two new alternatives. And then it continues in the same way. Look at the first alternative, and if no goals remain, then we succeed. And then remove the first alternative and continue with the remaining alternatives. And again, we look at the first alternative, and within that alternative, at the first goal, find all clauses whose heads unify with the goal and transform the alternatives by replacing the goal with the clause bodies. And we simply remove the goal if it can be derived via a fact, as in this case, and so on. So this is the default execution strategy of Prolog, and every Prolog system must somehow implement this, and ideally also make it efficient. And in this case, there are no variables involved, but we can easily extend it to also take variable bindings into account and report answer substitutions by simply storing the bindings together with each alternative. And the collection of alternatives can be naturally regarded and also implemented as a stack. Because we always remove the first alternative from the sequence and always add further alternatives at the beginning of the sequence. So that's why stacks easily enter the picture when implementing Prolog. And in fact, we can implement this more efficiently with two stacks instead of one. Because splitting this into two stacks allows many optimizations. And we call one of the stacks the global stack, which is also called the copy stack and also the heap. And we use this stack to store Prolog terms. And we call the other stack the local stack. And we use it to store environment frames and choice points. So these two stacks are the most important memory areas in Prolog. And in a real Prolog system, there are also other memory areas, such as the code area to store Prolog programs, then tables, often hash tables, to store functors and atoms, the trail, which is used to undo variable bindings on backtracking, and which can also be implemented as a stack. And of course, a Prolog system is free to implement additional memory areas if they are useful, such as, for example, a dedicated memory area to store strings, or maybe one for large integers, or one for cryptographic keys and so on. And maybe even with special access restrictions or different memory management strategies and so on. So the exact details depend on the Prolog implementation, but using two stacks, a global stack and a local stack, is a very common implementation strategy, and many Prolog systems use it. Now, let's take a look at these stacks. And we start with the global stack, where Prolog terms are stored. And the global stack, or heap, is an array of cells. So simply imagine a number of cells, each with a unique address, which can simply be an index. For example, here are 7 cells with index 0 to 6. And of course, an actual Prolog system can allocate hundreds of thousands or even millions of cells if needed. And the only limit is the available system memory. And of course, also how much of it can actually be addressed. And these cells are used to store terms. For example, let's consider a Prolog predicate p of x defined by a rule with only one goal, stating that the predicate holds if its argument x is a certain term, namely a term with principal functor f, and its arguments are a, b, and the third argument is a compound term with principal functor c and 2 arguments, d and e. And that's all. So we now have a Prolog program, and to execute it efficiently, let's compile the program to instructions for the Warren abstract machine, or WAM for short. And this abstract machine is named after David H.D. Warren, and it's tailored specifically for Prolog. Just like, for example, the Beam is designed for Erlang, or the P-code machine is used by Pascal and so on. And the WAM is of great historical significance for Prolog, because it showed that Prolog can be executed very efficiently. Of course, the WAM is not the only possible target for compiling Prolog, because there are other virtual machines, like the TOAM, used by bprolog. And you can compile Prolog also to native code or to JavaScript, as in Tau Prolog and so on. Yet the WAM is an especially popular target machine for Prolog, and several Prolog systems use it. For example, GNU, Scryer, and Sixtus use the WAM. And there's also a great book about the WAM by Hassan Ait Kachi, and you can freely download it from his page. Now, let's use, for example, GNU Prolog to compile this to WAM instructions, using the W switch of the GNU Prolog compiler, yielding the WAM instructions in the file p.wam. And here they are. So we see how our term from above is compiled to WAM instructions that reason about the term on the heap. And I say reason about because the instructions are general enough to both write and read the term on the heap, depending on whether the argument x is instantiated. So let's assume that x is a variable when the predicate is called. Then the predicate must create the term on the heap, that is, write it to the cells. And the term can be stored on the heap in a form we call linearized. This means that we first store the functor and then the arguments. So a functor consists of the functor name and an arity. And the arity tells us how many arguments follow. And in this case, there are 3 arguments, and they are written on the heap one after the other, each occupying exactly one cell. And in this case, the last argument is again a compound term, C, with 2 arguments. And so its functor is written on the heap, followed by the arguments, D and E. And now the entire term is stored on the heap. And each cell on the heap has a type. So for instance, in our case, the first cell has type str for structure. The next cell has type con for constant. Next cell is again a constant, then another structure, a constant and another constant. So each cell has a type, and therefore we can easily tell what's in a cell. And therefore unification can be implemented very efficiently in Prolog, because each instruction can quickly determine what's in a cell. So let's try a slightly different example where instead of this atom b here, we use the variable b. And also let's try it with Scryer Prolog, where we use library diag for diagnosis to get the WAM instructions of our predicate p as a list of instructions and print them with portrait clause. So here are the instructions emitted by Scryer Prolog. And what's notable here is that, first of all, Scryer Prolog uses different WAM instructions, such as put structure instead of get structure and so on. And also, the overall logic is different, because at least currently, so that may of course change in the future, but currently, Prolog constructs the term in a different way on the heap, namely starting with the innermost compound term, C of D and E. So it first puts this structure on the heap, C with two arguments, D and E, and only then it constructs the outer term, where we have the structure F with three arguments. First the atom A, then a variable, that's the second argument of the term, the variable B, and to represent a variable on the heap, we use a type of cell that's called a reference. A reference is a pointer that points to any cell by its address or by its index. And in the WEM, an unbound variable is represented by a reference that points to its own cell. So in this case, a reference to cell 5. And the third argument of this term is written on the heap as a reference to the compound term C of D and E that was constructed before. That is a reference to cell 0. So Prolog represents the term a bit differently here. And we know that this is not an optimal representation because it uses 7 cells instead of only 6 as in Prolog. So it's not optimal in terms of space efficiency, and it's also not optimal in terms of speed, because we see here that Prolog needs an explicit call of the equals predicate for unification of terms. And if you remember, Prolog didn't need that, because in Prolog the instructions were so cleverly chosen that the unification happened kind of implicitly due to the way the individual WEM instructions work together. So a key takeaway here is that there's often room for improvement in a Prolog compiler. And if you're interested in compilers, then you'll find many interesting opportunities in Prolog systems. And despite all such differences regarding space and time efficiency, we can still make a few general observations that hold for many or even all Prolog systems. First, memory usage of Prolog terms is quite intuitive and easy to understand. Of course, the details depend on the concrete implementation, but still, usually, one variable takes one cell. One atom takes one cell, which points to an entry in the atom table, where the actual atom name is stored and can be used whenever it occurs in a program. And a compound term with functor name f and arity n takes one cell for the functor, for an identifier in the functor table, then the representation of each of the n arguments, and maybe 0 to n cells for references to these arguments, depending on how compactly the Prolog implementation stores the term. So, even if there are differences between implementations, it's quite easy to understand how much memory a term takes. And there are no hidden surprises, for example, due to lazy evaluation, because in Prolog, terms come into existence simply by writing them down. And it's easy to understand, for example, that a term with many arguments takes more cells and therefore uses more memory than a term with fewer arguments. And what's also quite clear is that internally, terms are referenced efficiently and also pass around efficiently as pointers to cells. And therefore, passing around arguments of predicates is very fast, even if the arguments are very large terms, because internally only addresses of heap cells are passed around. So no matter how many arguments the term has or how deeply the arguments are nested, a term is internally simply referenced and passed around as an address, that is an index of a cell. And also, global stack space can be quickly reclaimed on backtracking, because we only need to keep track of the previous top of the heap and restore it on backtracking, so that everything that's accumulated on the heap can be forgotten and the memory can be reclaimed. And that's of course also very nice, because this somewhat reduces the importance of garbage collection. That's why, for example, Prolog is useful even though it doesn't yet have a garbage collector, because on backtracking, memory is efficiently reclaimed, also without a garbage collector. And as one small detail, we now also see why it's better to use terms with fixed arity instead of lists if the number of elements is known, because using a compound term with fixed arity is more memory efficient than using lists. For example, consider the list with two elements x and y, which is a compound term with principal functor dot, whose first argument is the variable x, and whose second argument is a compound term with principal functor dot and two arguments, y and nil. And if we represent this on the heap as in Prolog, then we first put this innermost compound term on the heap with a variable and a constant as arguments. And then we put the outer term on the heap, whose arguments are a variable and the compound term we've just put on the heap. So that would take 6 cells on the heap. And of course we can represent it more efficiently, like in GNU Prolog, where we start with the outer term and linearize it. So we write the functor dot and then the 2 arguments. And the second argument is again a term with functor dot and 2 arguments, a variable and the constant nil. And that takes only 5 cells. But even this more compact representation is not as compact as simply using a compound term f of x and y, or as is the convention for pairs, x dash y. Because that's a term with functor dash and 2 arguments, the variables x and y. And that takes only 3 cells, so it's more compact. But of course lists are still extremely useful, so don't get carried away with such micro-optimizations, because there are many good reasons for using lists. For example, because Prolog provides many built-in predicates and also DCGs for reasoning about lists. And there are, of course, also many opportunities for optimization. I mean, Prolog systems can reduce memory consumption in several ways. For example, speaking of lists again, let's consider an even more compact representation of lists, and also of partial lists. And let's think about it. For which kinds of lists would we really appreciate a compact internal representation? Well, certainly, for example, for lists and partial lists of characters, right? Because we'd certainly like to use Prolog for efficient parsing. And so it would be nice if we could use Prolog to reason efficiently also about extremely large files. And indeed, a Prolog system can represent such lists even more compactly. For example, we could introduce a new type of cell, say list, and use it to encode that at this location in the heap, a list element is stored. For example, here, the atom A occurs as an element in the list. And then we use the convention that the next cell on the heap is the tail of the list. Then, with this representation, we could encode this partial list with only 5 cells. But we can do even better, because we could represent a list of characters as a sequence of raw bytes using, for example, UTF-8 encoding. So in this case, we simply store the sequence A, B, C, D, terminated with 0, and pad the cell with zeros. And the next cell is the tail of the list. So in this case, a variable. And we represent the entire string as a reference with type partial string, pointing to the string. So this is how a Prolog system can very compactly store partial strings. Or as another example, a Prolog system could share subterms. For instance, if you have the term f of g of x, then clearly the subterm g of x needs to be stored only once. So we represent g of x as the structure g with one argument, a variable, and the outer term can simply refer to g of x in both arguments. And the beauty of this is that it can be done at compile time and also at runtime. So it also depends on the sophistication and trade-offs of the Prolog system. For instance, when I write it like this, then I certainly expect the system to share the subterm. And maybe if I write it differently, then it may not share it. And truth be told, calling this optimization isn't very accurate. Because in the literal sense of the word, optimization means that it can't be improved further. So maybe we should call all such examples only improvements. And in the strictest sense, maybe we should even call them trade-offs. Because certainly there are trade-offs here. For example, more compact representations of strings may decrease the speed of unification. And scanning the heap for sharing opportunities, of course, also takes computation time. However, I think in many cases the trade-offs lead to such great advantages that, given enough time and interest from Prolog programmers, an implementer will certainly make them. So it's fair to call them improvements. And as an aside, the way to implement improvements in Prolog systems is not to ask what is easy for the implementer and then require Prolog application programmers to cater to the whim of the implementer. Rather, a sensible way to implement improvements is to first ask, what do we actually want to do with Prolog? For example, We want to use Prolog for convenient reasoning about strings. We want to reason about partially instantiated data, and so on. And Prolog systems should support these use cases efficiently. And these use cases should guide implementers. And of course, the internal implementation of these features depend completely on the Prolog system. For example, in Scryer Prolog, the abstract machine is implemented in Rust. And if we look, for example, at the definition of heap cell value, then we see that this is currently a Rust enum type. And a heap cell can either be an address, an atom, or for example, a partial string and so on. And if someone is interested in performance, then they will certainly try to find a way to implement this more efficiently, so that a heap cell takes less memory in future versions of Scryer Prolog. And if you use, for example, a lower level language, then on 64-bit systems, a sensible approach would be to say we represent each cell by using 8 bytes, suitably aligned in memory for fast access. And so since each cell address is a multiple of 8, we in fact don't need the lowest 3 bits. And so we can use these bits for tagging to encode the type of the cell. And the rest of the cell is the value. So for a reference cell, it would be the address of a cell. And for a constant, it would be an identifier in the atom table. Or it could store a small integer value and so on. And based on this representation, we can implement a few optimizations. For example, we could use a displacement of the reference cell address to indicate that we are pointing to a list element. And that would allow us to not store the dot functor explicitly. Or for example, we could use specifically the tag 0 to indicate integers. Because if the tag is 0, then we can perform arithmetic, such as addition of integers, directly on the cell contents, even while keeping the tag. And there's also a nice paper by Andreas Krall, if you're interested in such optimizations. And even without such optimizations, we may need more bits for tagging. For example, because we need to distinguish between more types, such as big integers, partial strings, and so on. And on 32-bit systems, this can be a problem, because every bit we use for tagging means that the memory we can address is reduced by half. And in fact, we may need to reserve bits not only for tagging, but also, for example, for garbage collection, for marking. So we lose even more bits. And indeed, when 32-bit systems were more common, which wasn't so long ago, a common limitation of Prolog systems was that they could only use, for example, half a gigabyte for the global stack. And that would be a problem if you wanted to reason about very large terms, such as, for example, binary decision diagrams and so on. Now, luckily, these days are over, and Prolog is now a lot more interesting and useful for such tasks, because on 64-bit systems, we have many bits available for tagging. So let's turn now from the global stack to the local stack. And the local stack is analogous to what algol-based languages like Pascal and C call the stack. Because when Prolog proves one goal after the other, then it must remember where to resume execution when it returns, so to speak, from proving a goal. For example, suppose we have a predicate P of x which holds if some other predicate A of x holds and B of x holds and C of x holds, okay? Then in the default execution strategy, Prolog tries to prove the goals in the same order in which they are stated. So it would first try to prove A of x, and if that succeeds, continue with the next goal, and then again the next goal. Now, let's look at the WEM instructions of this predicate of P. So here are the abstract machine instructions, and let's place them here side by side with our Prolog program. Now, let's see what happens here behind the scenes. So what we see here is the code starts with an allocate instruction. This instruction means that a so-called stack frame is allocated on the local stack. And specifically, it's a so-called environment frame, or simply an environment. Because as we'll see, there are two types of stack frames on the local stack. And we now discuss environments. An environment contains the so-called permanent variables of the rule. These are logic variables that appear in more than one goal. And therefore, they need to be preserved between goals. So for example, in this rule, there's exactly one permanent variable, namely x. and therefore the allocate instruction is used with argument 1. The continuation pointer, which is a location of the next goal that must be executed after this clause is done. So in a sense, this corresponds to the return address, and a pointer to the continuation environment, which is necessary because the environments don't have all the same size in general, because they have different numbers of permanent variables. And once the stack frame is allocated and initialized, we proceed to the first goal of the rule. So first, the permanent variable is initialized, and then the argument register is set up for the call of A with one argument. And now it gets interesting, because control is now transferred to another predicate. And that predicate A could, for example, also allocate an environment and also invoke other predicates. And they, of course, can also allocate environment frames on the local stack. So stack frames accumulate on the local stack. And as the goals in the sequence are proven, the allocated environments are deallocated one by one. And then we end up with only our original environment, which contains the permanent variables of this rule. So if A of x has been successfully derived, then execution continues with the next goal, B of x. And so the argument registers are prepared again for the call. So in this case, there's only one argument, and then the predicate is called. And now it's the same as before, because the predicate B can also allocate an environment and invoke other predicates that also allocate environments. And as these goals succeed, the environments are deallocated, B succeeds, and we are back in our original clause again. And so execution proceeds to the next, and in this case last goal, C of x. So again, the argument registers are set up, and that's necessary because, of course, the argument registers could have been modified by the preceding goals or by any predicate that they have invoked. And now we encounter something interesting, because we see here that the last goal of a rule is handled differently than the other goals. Because we see here that the deallocate instruction is executed before the last goal is invoked. And this is called tail call optimization. This means that when the last goal of a rule is called, then the environment is already deallocated. And that's of course nice, because it means that the environments don't pile up for the last goal, even if the rule is used many times, for example in recursive clauses. So the effect of the deallocate instruction is that the current environment is removed from the stack, and only then is the last goal invoked. And we also see that a different virtual machine instruction is used for the last goal, namely execute instead of call, which in effect means that execution jumps to the definition instead of calling it and then returning. And jumping to the last goal is justified because there's nothing else left for this clause other than proving the last goal. So maybe aside from the straightforward tail call optimization, it's so far really quite analogous to the stack of other languages. However, with Prolog, there's a bit more to it, because as already mentioned, there are two types of stack frames on the local stack. Environments, which we've just discussed, these are for the control flow within rules, which we could call the end control flow, because within rules we have conjunctions of goals. And the second type of stack frames are called choice points. And they arise in Prolog because Prolog also considers logical alternatives. And we could call this the OR control flow, because different clauses are logical alternatives. Either one or the others must apply. So let's now take a closer look at choice points. They are used for storing logical alternatives and all the data we need for backtracking. For example, let's consider a predicate A, which has two clauses. One for the empty list and one for lists with at least one element. So that's a rather common situation. And let's look at the WEM code. So we see first, Prolog makes an efficient distinction on the type of the argument. For example, if the argument is a variable, then it jumps to label 1. If the argument is an atom, it jumps to label 2. If it's a compound term, which is not a list, it fails, and so on. And this is called argument indexing or simply indexing. So the Prolog system has a mechanism to quickly select matching clauses. And of course, the sophistication of indexing depends on the Prolog system we are using. So let's suppose now that the argument is a variable, that is the most general case. Then certainly both clauses need to be taken into account. So we can't simply consider only the first clause. And of course, unless we're using a parallel Prolog system, we also can't consider both clauses at the same time. And therefore, what the system does is it creates a choice point. This means that first it tries one of the clauses and it remembers that there's also a logical alternative, which it considers later. So we now run the following instructions, and if they fail, then we undo the variable bindings that they have created and run the instructions at label 3. And the choice point stores everything that's needed to backtrack to the current situation and proceed with the alternative. So this label here corresponds to the first clause, where the argument is unified with nil. And Prolog then continues with the next goal to be proved, whatever that is. And when all alternatives in that branch are exhausted, then the system remembers the choice point it saved above. So it backtracks to the previous state and then proceeds with the instructions at label 3, which is the alternative stored in the choice point. And since this is the last alternative in this case, it can be trusted in the sense that there's no other alternative that needs to be considered. And for example, if there were additional clauses to consider, then instead of trusting this clause, the system would simply update the existing choice point with information about the next clause that needs to be considered after this one. And that'd be a corresponding virtual machine instruction, retry me else here. But in this concrete case, we're already at the last alternative, and so the choice point doesn't need to be updated, but is removed. And the remaining instructions correspond to the second clause and so on. So at least with the when, to backtrack and continue with the next alternative, a choice point stores the argument registers, the current environment, that is its address on the local stack, which is stored in register E of the when, the continuation pointer, which is the value of register CP, the address of the most recent previous choice point, which is the value of register B, then very importantly, the next clause to try when the current one fails, so that's an address in the code area, the current trail pointer, and as already mentioned, the trail is used to undo variable bindings on backtracking. And the trail can be implemented as a stack, with the trail pointer denoting the top of the stack. And during execution, all variable bindings are recorded in the trail by pushing the address of each variable that becomes bound. And on backtracking, we only need to pop each address from the stack and undo the binding by overwriting the cell with a reference to itself. And we do this for all trail entries on top of this recorded value. And we also record the current top of the heap. Because on backtracking, we can simply forget everything on the heap beyond this recorded address. And as already mentioned, this ability to quickly reclaim memory on backtracking is one of the reasons why Prolog is so efficient. Because it doesn't need garbage collection for this, but simply resets the top of the heap on backtracking. And as already mentioned, environments and choice points are both stored on the local stack, where they are interleaved. And knowing a bit about choice points can be useful, because a Prolog system can apply some optimizations only if no choice points remain. And the most notable example is tail call optimization, because suppose that we allocate an environment as before and then invoke a goal. And now suppose that the goal leaves a choice point. For example, because it has multiple clauses and more than one applies. Or for example, because it calls another predicate that creates a choice point. And then the computation proceeds as normal, for example, allocating and deallocating environments. But the choice point remains. So if execution proceeds to the next goal, which may also allocate and deallocate environments, and finally we want to apply tail call optimization as before. That is, we want to deallocate the current environment before the last goal is invoked, then if a choice point remains, then the environment cannot be deallocated. And it's pretty clear that this has to be so, because on backtracking, when alternatives need to be considered, in this case for the predicate A, then the environment is of course needed again, because it contains the permanent variables of this clause and so on. So we say that the choice point protects the environment, and therefore the environment cannot be deallocated, because a more recently created choice point needs it. So it can be useful to avoid the creation of choice points, and of course clean representations can help with this. Because if you are using clean data structures, then Prolog can distinguish the clauses symbolically using argument indexing, and that avoids the creation of redundant choice points. Now, you may have a question at this point, and the question may be, why am I telling you all this? And just to make it perfectly clear, you don't need to know any of this to write great Prolog code. And I know this for certain, because just in the last few years, I've seen great Prolog code, also and especially from total beginners. And they knew nothing about any of this. They didn't know there's a global stack, didn't know there's a local stack, didn't know what an environment is, know what a choice point is, didn't know anything about tail call optimization. They knew nothing about any of this, and still wrote great Prolog code. Elegant, general, efficient, easy to understand, short, just great code, simply by following a few basic principles. And in fact, trying to understand Prolog at such a low level can even be counterproductive, because it doesn't scale. That is, you can only apply it to very small example programs. For example, consider a very simple definition relating a list to its length. Then how should we read this code? Well, I think it's clear that we simply cannot go through the code in the way Prolog does it. For example, we cannot understand it if we say, aha, now I perform argument indexing via a hash-based lookup, then I create a choice point, then I perform a few unifications, and on backtracking I remove the choice point, then I put a list on the global stack, then I allocate an environment, then I invoke a predicate for arithmetic equality and so on. So this simply doesn't scale. And we'd have tremendous difficulty to even understand such a simple and basic relation between lists and integers if we started to think in terms of stack frames and such low-level operations. So what we actually want is rather the opposite of this. Namely, we want to reason declaratively about our code and focus on the meaning, not on virtual machine instructions. So, for example, we'd like to be able to ignore one of the clauses and then reason about the remaining fragment of the program. Or, for example, generalize away a goal. So we want to work at the level of abstraction where we can ignore memory management, because the Prolog system should take care of it automatically. And that's exactly the point of using a high-level programming language. We don't want to be bothered with low-level issues. Or maybe more accurately, we want them to be implicit. So I'm telling you this mostly to reassure you of typical performance characteristics of Prolog. Of course, the details depend on the implementation, but at least for WAM-based systems, passing terms as arguments is fast, no matter how large they are, because terms are simply referenced via their addresses on the heap. So the Prolog system internally only passes addresses around. And on backtracking, heap space is quickly reclaimed, because the system only resets the top of the heap to the previous address, which is stored in the choice point. Also, tail call optimization avoids accumulation of environments by deallocating the environment before the last goal of a rule is called. And this is possible if the environment isn't protected by a choice point, which means that clean data structures aren't only good for semantic reasons, but Also good for performance, because they enable argument indexing. And that avoids redundant choice points. And that in turn allows tail call optimization. Also, lists of characters can be represented very compactly in memory, as raw bytes in UTF-8 encoding. So, if a Prolog implementer begins to argue with you that the system needs a special string type for compactness, and that you should now change all your Prolog code to their own custom dialect, then you know that they are simply wrong. Because strings can be implemented very compactly internally while still appearing as lists of characters within Prolog programs. And of course, many additional optimizations are possible. For example, sharing of terms, as we've seen above, or environment trimming, a generalization of tail call optimization, where we deallocate permanent variables as soon as they are no longer needed in any remaining call, or the tagging tricks I mentioned, and so on. And also, I'm showing you this because I'd like to invite you to contribute to a Prolog compiler, to make it more efficient, and also to add interesting features. For example, check out the systems I mentioned, maybe run a few benchmarks and look at the source code, and think about how their memory usage can be improved. Maybe add a garbage collector, or environment trimming, or sharing of terms, and so on. And that would make, for example, an excellent thesis project.